Like everything else about science, and thus entirely unsurprisingly, flat earthers don't understand how we know the dimensions of the Earth. Based on one distorted photo, they think the canonical shape of the Earth has been disproved. They dance around the fact that any flat Earth must also have a radius, like the idea is kryptonite, because that leads them into a host of problems we can discuss in a future video. For now, let's consider that the flat Earth stance on the Earth's radius, r, is an odd one. We're spoiled for choice when determining the shape of the Earth. The only difficulty is figuring out which method works best with your audience. If they prefer hard visual evidence, we have photos from space taken by humans like Earthrise, or the original blue marble, or by satellites like the Epic camera on Discover, or Himawari. What about indirect visual evidence like photos of a horizon? Or the shape of the shadow of the Earth during a lunar eclipse? Will they accept mathematical evidence like the Polaris observation or reciprocal zenith angles? Or are they into esoterica like the paths of seismic waves? And if your world is a sphere of some indeterminate size, it must have an R value due to the very nature of the geometric shape we call a sphere. Every sphere has a circumference, a diameter, and a radius. It's simply unavoidable. Since the Earth is very big compared to a human being, and the vast majority of us have no hope of ever going to an altitude high enough to see the curve of the Earth with our own eyes, we must make do with indirect evidence, either visual or mathematical. I'm going to try to get you from knowing nothing about the shape of your world to a good approximation of a radius for our spherical Earth. Something Nathan and Mitchell and others say is impossible. The first thing we need to do is to determine which model of the Earth we're talking about. The Earth is a natural object and is therefore imperfect. We refer to it as a sphere or a globe, but these terms are imprecise shorthand. The Earth is an oblate spheroid. A spheroid because it's very nearly spherical, but oblate because it's a bit wider than it is tall due to its rotation. But even that isn't sufficiently precise. The geoid describes the shape ocean waters would take under the influence of the Earth's gravity and rotation, but absent the impact of wind and tide, and as if extended through existing land masses. The result is essentially a very slightly uneven near sphere that is 0.33% wider than it is tall due to variations in the distribution of the Earth's mass. Precise calculations of location, distance, and dimension are possible if you query the WGS84 data. One online resource for this is the GeoidEval utility. Link is in the description. For ease of calculation, we idealize the geoid into the reference ellipsoid, which is the ellipsoid that most closely approximates the dimensions of the geoid. The ellipsoid figure accurately reflects polar flattening to 4 decimal places. I challenge any flat earther to truthfully tell me they can see the difference between the ellipsoid and a perfect sphere. We can use the GeoidEval calculator to tell us how closely the ellipsoid matches the geoid at any given point. We can see that at the North Pole, the surface of the geoid is 14.898 meters above the surface of the reference ellipsoid. The same calculation for the South Pole shows that the geoid's surface is 30.15 meters below the surface of the ellipsoid. This means the northern polar radius is slightly longer than the southern polar radius. Again, these are very subtle differences from the reference ellipsoid. If you were to scale the Earth down to the size of a billiard ball while retaining its geoid imperfections, you'd have a very smooth, seemingly uniform billiard ball. A second level of abstraction occurs when it's convenient to use a sphere in some calculation, so we define a sphere that most closely approximates the dimensions of the reference ellipsoid. Each of these models has its uses. The level of precision needed to find an unfamiliar location across town is much less than that needed to target a ballistic missile accurately, which is much less than the precision needed to track the effects of seafloor spreading. The second question is, which radius do you want to use? It should come as no surprise that the base assumptions of the reference ellipsoid and the sphere can vary depending on needs. For example, For certain uses, it might be better to dimension an abstraction of the geoid to most closely match the geoid's surface area. Other uses may require an abstraction based on matching volume. Differing abstraction types will yield slightly different radius measurements. Global radii are based on different definitions of the reference ellipsoid or sphere, as we'll see. Topographical radii are based on physical features of the geoid. Location-dependent radii are measured from the center of the Earth's mass to a specific location on the surface. The ellipsoid used for geolocation purposes such as GPS is based on the WGS-84 standard and has an equatorial length of 6,378.137 kilometers and a polar radius of 6,356.7523 kilometers. Because these are abstractions, it's not appropriate to express these values in the sub-meter units you would normally expect to use in geodesy. The nominal equatorial radius is the general use value. Unless you need something more specific, use 6,378.1 kilometers as the radius of the Earth. The arithmetic mean radius, known as R1, is simply a weighted average of the equatorial and polar radii. The authalic radius, R2, is based on a sphere that has the same surface area as the reference ellipsoid. The volumetric radius, R3, is based on a sphere that has the same volume as the reference ellipsoid. The rectifying radius, M sub r, is the radius of a sphere with the same circumference as the perimeter of any meridian or line of longitude. Topographical extremes provide another set of radii. The maximum possible distance from the Earth's center to a point on its surface is 6,384.4 kilometers at the summit of Mount Chimborazo. The minimum possible distance from the Earth's center to a point on its surface is 6,352.8 kilometers at the floor of the Arctic Ocean. The mean of all distances from the Earth's center to the surface is 6,371.230 kilometers, plus or minus 10 meters. Location-dependent radii depend on the location for which the radius is desired. Funnily enough, the geocentric radius is based on the geodetic latitude. Similarly, the meridional radius is based on the geodetic longitude. The prime vertical radius is based on the geodetic latitude and the polar axis. The key takeaway here is that the variance between the minimum and maximum geoid values is just 31.6 kilometers, or a bit less than 20 miles. This is about 0.49% of the WGS-84 model's equatorial radius. The geoid might be lumpy, but those lumps are very smooth. Let's look at an example, the so-called black swan photo of a highly refracted tableau comprising two offshore platforms, habitat on the left, hill house on the right. Here, the black swan is the photo on the left. You can see the distortion caused by the heavy refraction in the odd shape of the habitat boom at the left edge of the photo, as well as a miraging effect that elongates the platform vertically. The photo on the right is the same tableau at standard refraction. Habitat's boom now looks like it could do actual work, and the platform is realistically partially hidden by the horizon. Others have analyzed the photo on the right using various methods and found that the horizon is just about where it should be, assuming standard refraction. Let's look at the numbers for these structures. Platform habitat is located at these coordinates. Similarly, here are hill house's coordinates. At habitat's location, the ellipsoid radius is 6,381,532.8614 meters. However, the geoid radius is 36.3678 meters less than that per actual measurement, so the actual radius at habitat's location is 6,381,496.4936 meters. At hill house's location, the ellipsoid radius is 6,381,540.6467 meters, and the geoid radius is 36.2152 meters less than that, so the actual radius at hill house's location is 6,381,504.4315 meters. The ellipsoid distance between the two platforms is 5.17055 kilometers, and the difference in geoid radius between them is 7.9379 meters. Hill House is about 26 feet further from the radius of the Earth than Habitat. So not only do we have R, we have a millimeter precise measurement of R for each platform. Flat Earthers can't handle all the R we have. Flat Earthers claim to be pro-science and are always harping about the need for real-world observations, but they talk a better game than they bring. Their observations tend to be close to the surface sightings over water on high refraction days, and that's about it, really. The rest of their shtick is just the tendentious interpretation of real-world data using mutually contradictory ad hoc explanations that violate basic science. For example, Quantum Eraser, perhaps the chief proponent of the Black Swan, claims that the obvious refraction in the photo is irrelevant, that the real point is that the horizon appears much further behind Habitat than it should if the Earth were to have a radius of 6,371 kilometers. This is just blatant misdirection. The horizon is out of place because of all the refraction the distortions of the platforms make plain is there. What flat earthers have never produced is a photo of an out-of-place horizon on a clear, minimal refraction day. But I'll grant that measurements of the geoid from satellites aren't amenable to validation by flat earthers. So let's focus on two practical ways anyone can confirm for themselves that the Earth is more or less spherical and that its radius has a length, while acknowledging that these methods won't get you to the precision of WGS 84. The first method, involving simultaneous reciprocal zenith angles, gives you the shape of the Earth and an excellent value for R. To determine the Earth's shape, begin by establishing two surveying stations within sight of each other and find the zenith at each station. If the sum of angles A and B is 180 degrees, the Earth is flat. If the angles sum to less than 180 degrees, the Earth is concave. If the angles sum to greater than 180 degrees, the Earth is convex. Assuming the Earth is spherical, based on the prior observation, what is the radius? We've established stations within sight of each other, and we measure the distance between these two stations. At each station, determine the line that is plumb to the pull of gravity, then measure the zenith angle, which is the angle between the plumb line and the line of sight to the other station. To calculate R, calculate the complement of each zenith angle. Then use the angle-side-angle method to solve for the two remaining sides using the law of sines, where A is the unknown side and C is the known side. Rearrange to solve for A. Now let's work through an example. Bear in mind that the curve is exaggerated for instructional purposes. Establish two stations A and B, both located at sea level. The gray dashed lines represent local eye level at each station. The red dashed line is the reciprocal sight line. The distance between the two stations is 466.308144 meters. Next, we find our zenith at each station. The zenith angle, the angle between the sight line to the other station and the local zenith at both stations, is 90.00200969. We now have enough information to calculate the radius. First, we need the complement to each zenith angle. The complements to A and B are both 89.9979031. Next, we need the third angle, C. C is equal to 0.0041938. With all three angles, we can apply the law of sines to get the two remaining sides. A is equal to 6.37 blah 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 times 10 to the 6th, or 6,370,711.2 meters. Since angle B is the same as A, we know side B will be the same length as A. To check this against reality, we'd need to know the radius of the great circle route that passes through the two stations, but the volumetric mean radius of the Earth is 6,370,000 meters, so it looks like we've got a good answer. The technique also works if one or both of the stations isn't at sea level. You just need to remember to adjust the radius figure by the station's elevation. Another way to get a radius is to use Eratosthenes' method of calculating the circumference from the given data when we can get a radius from that. We set up a ratio, 0.00419388 divided by 360, is equal to 466.308144 divided by c, where c in this case is the circumference. Crunching the numbers, we find the circumference is very nearly 40,028,359 meters, and the radius is almost 6,370,711.2 meters. The delta between this method of calculating the radius and the law of sines is 1.4 millimeters. Not bad. Another method is to measure the surface of your world against an external landmark. You can do this with any object external to the Earth at optical infinity, but Polaris is conveniently located almost directly above the geographic North Pole, and we can use the standard geographic coordinate system to locate ourselves on the surface. Find a spot on your world where a bright star appears directly overhead. Stars are far enough away to be at optical infinity. The Moon is at optical infinity, so a star certainly would be in most flat Earth variants. This means the rays of its light arrive at the Earth following nearly parallel paths to each other. I'll show you how we know this later in this video. Measure the declination of the star. Ideally, the measurement would be 90 degrees. Let's call this point A. Pick a direction and start traveling. Monitor the declination of your star. If it doesn't change at all, you may be on a flat world. If it changes, keep going until the declination has changed by 1 degree. Note how far you've traveled. This is point B. Then keep going. Keep going in the same direction until the declination has changed by another degree, and note the distance traveled since point B. Call this point C. Repeat this process several dozen more times. Several outcomes are possible, but we're going to focus on one. Let's say that the distance traveled from point A to point B, from B to C, from C to D, and so on is always the same. There's only one geometric figure in three-dimensional geometry where such a one-to-one relationship exists between a distant stationary external marker and the observer's position on the surface, a sphere. As we know, a sphere has a circumference. How do we get a circumference length from our observations? The circumference is going to be 360 times the distance, where d is the distance traveled between points A and B, and between B and C, and so on, all of which are equivalent to each other. On a sphere, this distance we traveled from A to B is the linear distance equivalent of 1 degree of angular change in the observer's position. Let's say you had to drive 111 kilometers to have the star's declination change by 1 degree, making the distance from A to B equal to 111 kilometers. C is thus 360 times 111, so C is equal to 39,960 kilometers. That's our circumference. Now we need the radius. The formula for a circumference of a sphere is 2 pi r. Let's rearrange that to solve for r. R is equal to c divided by 2 pi. Substitute the circumference we already measured and solve for r. R will thus be equal to 6,359.83 kilometers. So that's one way of getting your world's radius. On Earth, we use Polaris, which is conveniently located less than 1 degree from the celestial North Pole. The distance required to change Polaris' declination by 1 degree is 111.13294 kilometers, giving a polar circumference of 40,007.86 kilometers and a polar radius of 6,367.45 kilometers. The difference from the WGS-84 ellipsoid's polar radius is about 10.7 kilometers, because the extrapolation is spherical, not elliptic. I've seen two primary objections to this process. The first is optical, holding that the change in declination is a result of some combination of perspective or refraction. While I handle this objection in more depth in my 4th video, the key point is that perspective is not a linear process, so that as the observer moves further away from the location of the 90-degree declination, the change in declination driven by perspective on a flat plane would deviate increasingly from the latitude. In other words, if the red line doesn't match the gray line, perspective doesn't save flat Earth. Also, typical refraction is wholly insufficient to reduce Polaris' declination to the observed values. On the left, the smooth blue line is the amount of refraction of astronomical objects as a function of apparent altitude above the horizon. By 10 degrees above the horizon, refraction is down to 1/10 of a degree, and it approaches 0 as your line of sight approaches 90 degrees. On the right, The dotted blue line is the apparent altitude of Polaris on a flat Earth due to perspective after correction for refraction. If that blue line doesn't match the gray line, perspective doesn't save the flat Earth. The second objection is methodological, that we shouldn't look to the skies to measure the ground beneath our feet. This is an odd cavil. For centuries, we've looked to the stars to understand our location as we travel over the Earth's surface. This is just an extension of that. Here's an analogy. You're in a room, but for some reason you can't measure the floor. You can measure the ceiling though. So you determine that the four walls are perpendicular to the ceiling, and the distance from the ceiling to the floor is uniform for all four walls. So you know your floor is some form of quadrangle parallel to the ceiling. You next determine that the angles at the corners where the two walls join are all 90 degrees, so now you know your floor is rectangular. Finally, you measure the length of each wall and find that they're the same length, so you've discovered that your floor is square. You've learned a lot about your floor, haven't you, without ever having measured it directly. As far as we know, the Greeks were the first to measure the circumference of the Earth, that being the famous Eratosthenes measurement of solar angles at Alexandria and Syene. Other Greek philosophers applied their own techniques and got not much different values, although the precise conversion of ancient to modern units remains a source of uncertainty. The Indian astronomer Aryabhata also measured the circumference, as did Arab astronomers Al-Khwarizmi and Al-Biruni, with similar conversion issues. How accurate these measurements were depends on which historically attested conversion you use from ancient to modern units. In the modern post-Renaissance era, measurements were undertaken to improve navigation and as part of the development of the metric system, leading to the development of the nautical mile and the kilometer. The latter idea was that 1 kilometer would be 1/10,000th of the distance from pole to equator. Because the Earth isn't a perfect sphere, and the slight irregularities of the geoid couldn't be measured with contemporary techniques, the standard kilometer is just slightly too short, and the polar circumference is 40,007.863 kilometers, which is based on the rectifying radius. A practical application of this technique involves a comparison of the distances between the bases and the apexes of the main support towers of long suspension bridges. Without going into too much detail, the weight of the roadway of a suspension bridge is borne by the cables, which are then essentially draped over the towers and anchored at each end of the bridge. The bridges are designed in such a way that the forces on either side of the tower are equal. The tower stands on a line plumb to the pull of gravity and perpendicular to a tangent line at its base. If it weren't plumb, the compression forces on it would point outside the tower's base's footprint, destabilizing it. This makes sense. A perfectly vertical stack of Legos, for instance, will stand erect on a tabletop without being anchored to the surface, while a similar stack configured to lean toward one side will not. Which of these stacks is more stable given a downward force on the top block? If the world is flat, then the two towers, which are plumb to the pull of gravity, should be parallel. If curved convexly, the apexes of the towers should be slightly farther apart than the bases. The Verrazano Bridge in New York has two main towers 211 meters tall and 1,298 meters apart at the base. The apexes are 4.1275 centimeters farther apart than the bases, so we already know the Earth's surface must be convex. In effect, we have a trapezoid where the two sides are parallel and the other two are angled toward each other. The parallel sides are 1,298.041275 meters and 1,298 meters long respectively, and the angled sides are 211 meters long. We can find the implied length of the two angled sides to the point of their intersection, and thus the radius of the Earth by multiplying the height of the towers by the length of the base and dividing the result by the excess distance between the apexes. Radius is thus base times height divided by excess, or 6,635,445 meters. The radius at latitude 40 degrees, 36 minutes, and 23 seconds north, the location of the bridge, is 6,369,122 meters for an error of 4.18%. This represents a bridge measurement error of 1.73 millimeters over a span of 1,298 meters. This same observation could be performed on other long bridges such as the Humber in Yorkshire. For fun, you can calculate the expected variance between base and apex distances for any suspension bridge. You need the height of the bridge's towers, h, the distance between the bases of the two towers, d, and the bridge's latitude in radians. You'll also need the radius of the Earth at the bridge's latitude, which is the following calculation, where RE is the equatorial radius of 6,378,137 meters, and RP is the polar radius of 6,356,752.31424 meters. Plug the final value of RB into the following formula. Variance is equal to h times d divided by RB. Taking the Humber Bridge in Yorkshire, England as an example, the height of its towers is 155.5 meters. The distance between the tower bases is 1,410 meters. The latitude of the bridge, which is 53.7064 degrees north, is 0.9374 in radians. The radius of the Earth at that location is 6,364,286 meters, and the expected variance between the bridge's base and the apex distances is 34 millimeters. The actual variance is 36 millimeters. How do we know that light rays from a distant object are nearly parallel when they arrive on Earth? From our vantage point on Earth, the star is a point source of light, so we can treat it as the apex of an isosceles triangle, where the two equivalent sides have a length of the distance to the star, and the base has a length of the diameter of the Earth. Having the lengths to all three sides of the triangle, we can use the law of cosines to solve for the angles. We solve for angle A by taking the inverse cosine of the right-hand part of the equation. We're interested in angle A because it will tell us how close to 90 degrees, to parallel, the light is when it arrives on Earth. Remembering to convert the diameter of the Earth to its equivalent in light years, we plug the numbers in. The squares of the distances to the star cancel, leaving only the Earth's diameter in the numerator. This leaves us with a very small number in the denominator and an absurdly small number in the numerator. Divide and take the inverse cosine to get angle A, which is so close to 90 degrees that the human eye could never perceive the difference. No visual measurement and very few instrumented measurements would be affected by the difference. It's effectively parallel for all practical purposes. Clearly, the diagram is not to scale. We followed a logical progression. We began by determining the shape of the Earth using zenith angles. Two plumb lines that aren't parallel to one another demonstrate the Earth can't be flat. The lines separate with increasing altitude, so we know the Earth is convex. Because this operation applies consistently throughout the world, the Earth is known to be spherical. Next, we establish a radius again using the trigonometry of zenith angles. There are two sources of potential error here. The first is that the measurement itself could be flawed, which is why geodetic surveyors take multiple measurements and calculate a potential error. A skeptic would need to show how the measurement was flawed and, ideally, produce competing measurements taken under similarly rigorous conditions, showing that these zenith angles are actually parallel. No flat earther, to my knowledge, has done this. The second is that trigonometry somehow doesn't apply in this scenario. Good luck with that. We use known or estimated distances to celestial objects to calculate how parallel are the rays of light coming from them. The more distant the object, the more parallel its light when viewed from Earth. The moon is 238,000 miles away, and its light is less than 2 degrees from parallel. The sun is 93 million miles away, and its light is less than 5/1000ths of a degree from parallel. Scientists prefer to perform multiple observations, preferably using different observational techniques, to establish the initial observation's accuracy. In this case, we have an initial observation that the Earth is spherical by using zenith angles. We test that observation using a different technique, the Polaris observation, and confirm the original conclusion. The Earth really is spherical. If the Earth is spherical with the radius we've calculated, then this fact will have some practical effects. For example, long man-made structures that are intended to follow the Earth's surface should display the same curvature. Long suspension bridges are excellent for this purpose, and indeed, we find that their towers, which for engineering purposes must be plumbed to the pull of gravity, are further apart at their apexes than at their bases. A bit of math with these bridge dimensions result in a radius very comfortably near the radii, as measured using other techniques. We thus have a web of mutually supporting observations very strongly indicating that the Earth is a sphere. In science, we provide evidence, not proof. Proof is a mathematical concept. The irony is that the flat earthers demand proof of the shape of the Earth, but when it's provided, they claim the proof is in the maths, not in real life. There's plenty of R out there if only flat earthers would bother to look.